Hi, astronomy students of Astronomy 1A at RCC. This is to share with you another video concerning the solar system, basically. I know we talked about this one last time around, that there was a part 2. I'll try to keep this video probably less than 20 minutes, hopefully. Anyway, this is a software called Universe Inbox. It gives me a simulation of the solar system. What you see in here, if I can get closer to it, is the solar system, centered of course around the sun. I have here different objects that I'm looking at. These are the inner planets, of course. You have Mars in here, and Earth, Venus, and if I can see where Mercury is, somewhere in here. Here is Mercury. Anyway, these are the inner planets. The outer planets start from Jupiter, Saturn, and then if I zoom out, of course, I will see Uranus in here, and actually Neptune in here. Pluto is actually a dwarf planet, and it's part of a different structure. One of the features that all of these planets share, and this is the fact that all of them exist on the ecliptic, at least the planets do. And the other objects that deviate from the ecliptic are smaller objects, and there is an explanation for that, of course, when we talk about the formation of the solar system. And actually, we talked about this when we talked about the conservation of angular momentum, is that this object need to remain on the same plane. And that is basically the plane where all of the big objects are. Smaller objects get knocked off of their path, and that's why they are off of their path. Like, for example, Pluto. Pluto is not on the same plane. Sometimes its path takes it crossing the ecliptic, and sometimes comes back. And actually, not even the big object, they are not exactly 100% on the plane itself, and that is another phenomenon that can also be explained by collisions. Anyway, let me zoom into Earth in here. I want to go back to it and see if I can find it in here. Okay. One of the features of this software, it gives you more information if I click on the object. Right now, I'm looking at the Earth at a distance of, how far are we looking at it? Of a little over the distance from the Earth to the Sun. This is how the Earth would look like. Let me remove this traces so that you can see it. And let me remove the label. You see here? This is where the Earth is, but it actually gives you all of that big circle. But if I come closer to it, watch this number in here, how far we are from it. Right now, we're getting closer. We are at about, what, 48 million kilometers, so still too far, okay? And at a distance of 10 million kilometers, this is how the Earth would look like. Not much, doesn't it? Now, at a distance of a little over a million, this is how the Earth would look like. Now we are at the distance shade outside of the moon. So this is roughly how it looks like from the moon. If you are sitting on the moon or standing on the moon, this is how the Earth would look like. I can put this number in here. Let me put it, the distance from it to about, I don't know if I can't enter it manually. Anyway, so this is how far it is, how far we are from it. When the astronauts looked at it, this is how they looked at it when they were looking at it on the way to the moon, when they were going to the moon. This is almost midway between the Earth and the moon, 167,000 kilometers, where the distance from the Earth to the moon is about 370 something thousand kilometers. Now, if I come closer to the Earth, right now I don't see much of the features of the Earth. So if I come closer to the Earth in here, this is how it looks like. This is, we're looking at the dark side of the Earth right now, because we're coming from behind. We're not coming from the sun side, the sunny side. The thin layer, right now we are at a distance of 28,000 kilometers, just a shade inside of the where the satellites are. This is that shaded area that you see in there. That is actually our atmosphere. You see how valuable the resources we have. This one, it makes it a very, very, valuable and precious place that we live in. This atmosphere is required for life on Earth to prosper. Otherwise, without it, life will end as we know it. This is at the distance of 18,000 kilometers. We're still very far away from it. We're looking at North America right now. And one of the features of this software that gives us actually some information on it, namely the the eccentricity of the Earth. The eccentricity, this is related to an activity we did in classroom. The eccentricity of the Earth is 0.016. Okay. Remember when you guys calculated your eccentricities for your own ellipses that you made in the classroom, they were all very high. They were 0.2, 0.3, and so on and so forth. Those are very, very ecliptic paths. Of course, the closer, the higher it is, the more ecliptic the path is. If I look at different objects in the solar system other than the Earth to see how eccentric they are, how basically how the paths are, relatively speaking. Let me turn on the names because right now I need to know what the other objects are, otherwise it's very hard to find them. They're too small. So let me turn on the labels and turn on actually the paths also to see them. So here is Venus. Venus's eccentricity is a lot smaller than that of the Earth. In other words, its path is far more circular than that of the Earth. Mercury is kind of odd a little bit, but its path cannot really be explained 100% by using classical mechanics, namely the conservation of angular momentum, because it's actually too close from the sun to be explained by that. You need relativity for that. In the case of Mars, it's 0.09. It's far more eccentric than that of the Earth. Remember, the Earth is 0.016. This one is about what? More than 4 times or something like that bigger. Jupiter, which is here, that Jupiter is 0.04. It's a little bit more eccentric than the Earth, but still, it's almost circular path. Same thing for Saturn. If all of the objects in here that are big objects in the sky, and where is this is the path for Saturn. Oh yeah, Uranus is very far. Uranus actually is still very almost very close also to a circular path and an elliptical path, and so is the eccentricity for Neptune. It's very close from that of the Earth. Pluto, on the other hand, it has a very high eccentric path because it's a smaller object and its eccentricity is very big. It's almost similar to some of your ellipses that you guys drew, which is 0.25, which is a very high eccentric path. So it's very elliptic path. Remember the measurements that you guys did in classroom. If I take any other object, like for example Makemake, which is a different object in here, this is Pluto, Makemake, Haumea, all of this are part of the dwarf planet classifications. They are not actually planets. This is very high. Remember, the Earth is 0.016. This is 10 times bigger than that of the Earth. It's really ecliptic. The path is more ellipse. And look at the path in here. It's completely passing through the ecliptic. Another feature of this software in here that is very useful for us in terms of the density. For example, if I compare Makemake, since I have it in view in here, it's very light. If I look at Saturn, for example, what is the density of Saturn? The density of Saturn is, if I can find it, the surface, it's 687 kilograms per cubic meter, or 0.687 grams per cubic centimeter. It's lighter than that of the water. Water is 1,000 kilograms per cubic meter. In other words, if you take Saturn and put it on the ocean, if you can of course fit it on the ocean, which is impossible, it's too big for that, it's going to float. Jupiter, that density is 1.3. It's a lot less dense than that of the Earth. Actually, the Earth is the densest object in the solar system. 5.51 grams per cubic centimeter. Super dense. For the big objects, of course, I'm talking about. Venus is less dense, 5.24, and the next object that is very close from the density of the Earth is actually Mercury. Mercury is super dense, and one of the theories about Mercury that's going on around right now is that actually it used to be a Jupiter-like planet, and then it lost all of its atmosphere, and now it's basically what is left is its inner core, basically. Mars is less dense than the Earth. Mars is 3.93 grams per cubic centimeter. One of the missions that is right now ongoing on Mars is InSight. The InSight probe is taking measurements of the Martian quakes, and the theory that is going on right now is because there are a lot of activity, is that apparently Mars is settling down. It's actually going down and down, and its density is apparently going to increase over time. This is some of the information that you get in here. One of the other features in here, if I let time evolve, you will see that the planets will move at different rates. The closer they are, Mercury that is, for example, will move faster than anybody else. Let me have an overview from the top in here to see how this motion look like. I'm going to start time. The time is going to be moving super fast right now. It's 17 days for every second on my computer. And you will see Mercury, for example, it's here, has already passed, but let me, since we are focused on the, let me bring the sun to focus so that we're looking, so that this animation doesn't go anywhere. Let me close this one. Anyway, you see here, Mercury is moving faster than you have Venus, which is moving fast. After that, Earth. Mars is still moving. Vesta and all of the objects in the asteroid belt, actually, where is Sirius? Sirius is the biggest of these objects in here. Yeah, here it is. So it's moving inside the asteroid belt in here. This is part of the structure between Jupiter and Mars. And you can see that Mars is a lot slower. And that is one of the projects that you guys are working on right now, is that the Earth is overtaking Mars because the Earth moves faster than Mars. And that's what the explanation for the retrograde motion for the different planets. At some point, also Venus will overtake Earth because it's moving faster. And as I move further away in the path in here, you guys see this is the second law of Kepler, namely that the closer you are, the faster the object is going to move, basically. And or at least the third law, actually, where the period is actually, the period squared is proportional to the distance cubed, and that is because these objects are further, so they take a longer time to spin around the star, or around the sun in this case. Look at Saturn. At the same time that Mercury inside has gone through several cycles, this one did not even budge from its place. Uranus, on the other hand, will be hardly moving. I mean, Saturn will appear to be moving a lot more, and so Neptune in here in this case. Any post-Neptunian objects in here, they will appear to be a lot moving slower, including Planet 9. Let me go back to the Sun right now, and let me click on the Sun right now. I'm not clicking on the Sun, I'm clicking actually one of the asteroid belt objects. And here is the Sun. Right now we are, and let me bring it into focus in here. How far are we from the Sun? We are looking at about 31 astronomical units. We're not too far, really. We're still within the solar system, well within the solar system. At 70 astronomical units, this is how the solar system would look like. At about 200 astronomical units, this is how the solar system would look like. Let me go a little about 500 astronomical units. This is 600-700 astronomical units. This is how the solar system would look like. If I remove the trails in here so that we don't see any, or at least the labels, this is, if you are on planet 9, this is how the solar system would look like to you. It's very far. It's very difficult to look at it from very far away distances. That's why it's very hard actually to find where this planet 9 is, because even a small deviation would be very difficult for us to see its location. They're having very hard time trying to locate it, but we know, according to a lot of models, that it exists, but we're having difficulty finding it. Let me put the labels back to find where my objects are in the solar system. It's very difficult to find it without any labels. So again, here is the Earth, and at the Earth perspective at this point, we are on, actually the date has moved to June. I have to reset this animation and go back to where we came from. So let me go back into where we started in here. So I'm going to reload. So it's going to take a little bit of time to reload. Yes, reload. And once we are reloaded, I want to pause this, and I want to come to today's date to show you something that we're going to use right now in the Stellarium. software to try to find where my objects are in the sky. Again, we are in the year 2020. The month is actually 03 and the day is 22, and we're gonna go into 2040 around 8:40 in the evening. So once we reach that time, we're gonna stop. Okay, so this is tonight. Tonight on the Earth, looking in, we will see Venus in the evening. We will see Mercury in the morning, just before when the sun starts to rise. And then we will see in the evening, lined up together, in the morning actually, we'll see Mars, Jupiter, and Saturn, all of these three objects. Uranus and Neptune, they will be too faint to be seen anyway with the naked eye. So let's go and see from the Stellarium perspective how that looks like. So I'm going to turn on the Stellarium software. Stellarium is actually what we will see, what we actually see, not models based on physics or anything like that. So I'm going to go to 8:30 in the evening. I'm sorry, not 8:30. It has to be military time, so it's 20:30 is fine. So this is how the sky looks like. This is, we're looking at sunset. Look at Venus right now. It's in the sky. Venus is super bright object in the sky. It's not a star. Again, this is where Uranus is, but we can't see it with the naked eye. This is basically what you will see with your own eyes. The sun already set in the west, so we are looking at 8:40 or 8:30 in the evening. So we are looking at 8:30 and 8:36 in the evening. The southern sky, the brightest star again is Sirius or Ceres in here in Canis Major. One of the interesting objects that we will see still in the night is going to be Orion's belt. Here is the belt itself. Here is Orion, the constellation itself, Rigel, Aldebaran, Bellatrix. If you extend Bellatrix, you will see Aldebaran. Aldebaran is, did I say Aldebaran? This is Betelgeuse, I'm sorry. And this is Aldebaran. It's part of the Taurus constellation. Actually, it's the eye of Taurus. This is where the hunter, this is his shield trying to hunt for the Taurus. Canis Major is his dog, and here he's using it for hunting. One of the features that I'm going to try to zoom in on it in here, and this is if you go to big telescopes, for example, the one in Los Angeles in here will show you this constellations, or at least, I'm sorry, this globular, this, the word escaped me right now. This nebula, this is where the stars are forming. Actually, if you zoom in, this is actually a lot of clouds in here. This is where the stars are forming, a lot of young stars. I mean, for us in the naked eye, it looks like it's only one star. But there are a lot of stars in here that are forming, and some of them are just turning on. I'm going to zoom out in here to see how it looks like to us. This is how basically it looks like to us at night in here, looking at the sky. Again, Ceres is here. And this is what the nebula look like from distance. Let me go back into the east right now, but before I do that, I want to animate around the North Star. Again, this is where Polaris is. The angular distance from the horizon to Polaris is about 34 degrees, 33 degrees, 58 minutes. This is the altitude. This is our location here in Riverside. Again, all the objects in the sky will appear to be moving around Polaris. So if I'm going to animate this one, I'm going to come in here and make this night move faster. And you will see all of this is actually Cassiopeia. You will see all of the objects in here, including all of these constellations and stars and everything, move around. Again, this is the structure for the constellation where actually Polaris is located. Polaris is part of the Ursa Minor. Anyway, so let me animate this one and make it go fast so that we're moving to see how the sky would look like if you wait long enough and take a note of the object. Don't pay attention to those fast-moving objects. They're actually satellites, but this is how the sky would turn and move as you look at it. And here again, the value of Polaris is that it's not moving. You can see all kinds of stars in here, except it won't be moving because the entire sky appears to be revolving around it. Right now we are 3 o'clock in the morning. Vega is very, very bright and seen in here. Its luminosity is actually very, very, very high. but not as high as that of Ceres. It's a lot brighter than Polaris. Polaris is 1.95. This is 0, and 0 is much smaller than this number in here. That's why it appears to be brighter. Remember, Ceres is a negative number, so that's one of the things that you have to remember is that. And you will take it in astronomy. V is that the magnitude has to do with the brightness of the star. At this point, Altair is actually another star that we're monitoring very closely. It's a super bright star, and it's about 16.7 light years away from us. One of the interesting things in here about this star is they are gone already in the south that I was talking about earlier, is that some of them appear to be. Antares is a supergiant star actually, and it's 500 and something light years. Let me go back into the eastern sky. I was hoping to see some of the planets appear, but we are 3 o'clock, 3:30 in the morning, and none of them appeared yet. So I'm going to move time a little faster and see as the planets start to appear. Okay, so it's 3:04, so it's not moving that fast. So now objects rise from the east, as we said in class, because the Earth is moving actually from the west to the east, rotating, spinning from the west to the east. Barely Jupiter starts to be seen, and again, remember from the previous animation, we should see Mars and Saturn not too far from each other and the sky. So now, around 3:40 in the morning, Saturn rises, and Jupiter actually rises also, and Saturn also is visible. If I wait long enough, I will see more objects. Let me stop in here and see if I can look at Jupiter. It's barely above the horizon right now. It's where is its altitude in here? It's increasing, of course, because it's still rising. So if I look at it with the telescope, this is how it looks like. You have Ganymede, one of its moons, Callisto, another moon, and Europa, another moon. Remember, when Galileo looked at this system, he saw, or at least the Jupiter, he saw 3 moons. Those are the 3 moons he saw, and the day after he saw the 4th moon, Io. So where is Io, you ask? Io most likely is hidden behind right now. It's still behind Jupiter. So if I'm gonna do what I'm gonna do is I'm gonna remove the this one in here. I'm gonna let time evolve a little bit. So go a little bit in the morning to see if I can see. Let me move faster, because I expect around 4:30 or something in the morning. Probably we should be able to see Io. Okay. Right now we are 4:30 in the morning. So let's stop this and let's look at. I don't mean that. I don't want that. I want to be focused actually on Jupiter. Okay, what do we see now? We're still Io and Europa, they are one behind the other. Again, that's how basically they appear in the sky. So all the 4 moons, you can still see them with what looks like it's in here. What I'm using in here is a telescope to zoom in onto this planet. Let me zoom out and let me remove this. So if I look at Jupiter up close, this is how Jupiter starts to look like. Okay, now the moon starts to appear visible, and so this is where zooming on it, and actually this is where it looks like Io is far, but it is not. This is the angular view, that's all, actually, because Europa is very deep, very far compared to Io. Io is the closest moon of Jupiter, and this is what Jupiter would look like when seen from up close in here using this animation. Okay, I hope this is useful. I'm going to stop it in here because I don't want to make it too long. And we'll talk about this ones later on, especially in terms of your project and things like that. I hope I'll see you guys on Tuesday online. And if you have any questions, we'll discuss them there then. Thank you.